Okay, so now we can finally start. So for course, the score, let's just go. So the grading formula is 0.35 for the homeworks, average grade on homeworks. So there is a deadline every odd lecture. So now is first lecture, okay, you didn't have any task, so it's good. But the third lecture, you will need to solve the task from first and second seminar. And beginning of fifth or third and fourth seminar, and so on. So every seminar has 2 homework tasks, and then it has extra homework task. So if you make extra homework task, it will be added to the score of final exam. So half point for each task. So then the second is colloquium. So there will be a list of 16 questions. So there will be 1 or 2 questions from each lecture, and it's just the main theoretical result. And I skip first lectures because it's basic stuff, but from other lectures, and so the proof to prove, and then a few questions come from seminar. Okay, you get the list. Ask me 2 weeks in advance. I should give it, but usually I'm very busy in December, and so you need to pressure me, and it's okay. And so and then, but most students who know the answer have 10 out of 10 for colloquium. So if you learn everything, it's very easy if you do the effort. And then for exam, questions are a bit harder, and it's open book. So colloquium, you can only bring 1 sheet with some definitions on one side that you tend to forget. And here you can use the books. So there are 3 books. It's Zipser book. It's a very old book, but it's written in the time that people knew little, and it's very simple. And so that's why I choose it. So we will speak about Turing. So chapters 3, 4, and 7, 8 will be most important chapters. So if you learn them, you will have good, 6, 7, you will be fine. And then there will be a few more results or a few different things. So that's the main references. For people in theoretical computer science, so if you find Zipser book too easy or already solved many exercises, so then good students, they try to read it from this book. So it starts from a bit higher level with concise definitions, and then you can use for many other courses as well. So this is by Aurora and Barak. So, and then there is very nice book. So it starts very low, many explanations, and it ends in very difficult level. And so the many topics we learn here are also in this book, and they speak about history and some things that were popular and sometimes. Okay, and they're just very beautiful examples. And so if you have but the disadvantage is too much information. It takes a lot of time to read it, but it's very rewarding. So I'm also still busy reading it. So whenever I have time, I can recommend it. So the other 2 books seem way more popular, but I hope this one I warmly recommend. So it's people who want to have nice atmosphere for teaching. So they have very beautiful pictures. Okay, so yeah. So it's the nature of computation by Moore and Mertens. And so all information of the course is on the Wikipedia. You know about the wiki, right? Everyone, yeah. So please, so in Telegram, there is Telegram channel. The invite link is on the wiki, so I hope everyone already subscribed. And there are a lot of questions in the first weeks of the lectures, but all these answers are usually on the wiki. So for 5 times in every course, I have to type, please, this is the answer. It's also on the wiki. So, okay. Yes. And then, so what's the goal of theory of computation? So the question is, will you need this? And so I must say that for most jobs in IT and data science, the first 5 years, you will not need anything you learned here. So why do you learn? Well, the interview questions, sometimes they ask about NP hardness, which is one of the main topics here. Or sometimes they give you programming task, and if you recognize it's NP hard problem, then you think you're clever, you solved it with polynomial time algorithm. If you know about this theory, you have alert in your mind to check again. But okay, I never did such job interviews, but there exists a book about interview questions I found on the internet. There are quite some questions about NP hardness, although it's not so relevant. However, something changes, like although I'm not professional programmer, I was in charge for a programming project with several programmers. And so there was some optimization problem we had to solve. And then everyone is proposing ideas. And so we get NP complete problem, and we want to solve it. We want to have solutions that are provably correct. So the algorithm doesn't need to produce the answer always, but if it produces an answer, it must be correct provably. So that was the task. So it should provide the answer plus the proof. And so then there are 2 years, there was weekly meeting, and in half of the meeting, there was somebody, like we transformed the problem to a special case that solved in polynomial time, but then go back to NP hard problem. So every 2 weeks or something, I had to shoot down some idea, because I say, look, this reduction, it will never work because you make the problem harder again instead of easier. So I think later in the career, it becomes more important, especially for research directions. And so now there is something happening that happens every few years. So machine learning algorithms are improving. And so people think all these algorithms are not longer needed. There will be a machine learning model that solves it optimally. And so it's a recurring idea every 10 years or something. So now in the stock market, all this chip and computer companies, they're huge, and currently they're crashing because people understand that ChatGPT is not what they expect. And so, but it's nothing new. So maybe there will be 2 other waves like this, but then finally, I mean, at some point in future, okay, this is very philosophical. These things improve, and maybe they can generate, I can do research in IT, but at the moment, this is not the case. So, yes, okay. So, well, so I already explained what's the goal of the course. There will be problems, algorithmic problems. In practice, they're messy. Here in class, they will be simplified so that I can communicate them in just a few minutes. For example, such a problem, take a social network like Facebook or Instagram or whatever thing you're using. And you can ask the question, can you find 300 people that are mutually connected to each other? It was actually an old way to find fake accounts. So fake accounts tend to form cliques. So people who make these algorithms are not so clever, and so it's easy to avoid cliques by just randomly refuse to connect with someone. But okay, that's old algorithm. They try to find cliques. But the question is, if there is billion nodes, can you find? So a clique is a set of nodes in a graph that are pairwise connected. So every pair of nodes in the set is connected by an edge. And so there is a question, can you find 300 people, 300 nodes out of 1 billion that are all pairwise connected, form a clique? And so in this course, you will understand that there is no hope for such algorithm. So even if you allow 1 million CPUs running for 1,000 years, there is no algorithm that gives a provably correct answer to this question. So in this course, we are speaking about distinguishing hopelessly difficult problems with the ones solvable in polynomial time. So like sorting is almost linear time. So usually if there is a polynomial time algorithm, you can optimize a lot in practice and make it work. There are some famous exceptions like linear programming that, yeah, that's kind of pain in the ass. So sorry for the words. But usually if you're outside these NP-hard problems, ideas come from algorithms. If you deal with a very difficult problem, you need to change the problem or get some heuristic idea, like an idea, this heuristic might work. It's completely different research. So in one time is how to make things, algorithms I have faster. The other will be like, what is the secret? Some research is needed to notice that graph is like close to a tree and then use some tree with algorithm or anything. Okay, so what will be the course? So first 7 lectures will probably about NP hardness. Then we will speak about a few other classes and a few other difficulty classes. So, so there are some problems, especially like optimization problems with adversarial settings. Like they're not NP hard, they're P-space hard. They're very important for theoretical computer science people. So we will study that. We will also study about circuit complexity, which is also important in practice, like how your computer computes addition and multiplication. But for theoretical, this is very important model because it's like our only hope to settle problem P versus NP probably comes from circuit complexity. Well, it's connected to everything. And then in the last lectures, I will speak about parameterized complexity. This is once you know your problem is hard, what are the techniques? Are there nice mathematical techniques to find solutions quickly? So we will speak a lot about reducing the size of the problem. So there's some nice techniques about it. And this will be from different books. So nothing of these books, this is quite something recent that become this discovered to be very useful in industrial research for combinatorial optimization. So, but nothing of this will be in your combinatorial optimization course. There will be a bunch of other techniques there. So it's disjoint. So note that this formula is for people in applied math and informatics. So for software engineering, there is a third part in the third module. So there will be 0.3 for homework, 0.3 for colloquium, 0.2 for exam, and 0.2 for the project on parameterized complexity, which is in the third module. So they need to program something. Okay, so now blah blah. That's all the technical things. You know what you can expect from the course.
Excuse me, how many points can one get from extra homework? So points for extra homework goes for exam.
Yeah. So for exam, it's graded out of 10. And each extra problem from homework is 0.5 out of 10. So I think like 8 or something.
8.
Yeah.
So basically you can just skip an exam. Do a lot of
Yeah, and this also there is auto grade. So if I see you need only 6 out of 10 to get final score 10 out of 10. So there is rounding. So nothing is rounded until I need to transfer to official grade, which is when I'm forced to round. And then it's arithmetic rounding. So if the non-rounded grade, so if this grade is at least 0.9, so assuming you have 6 out of 10 gives you 0.9 out of 10 on final grade, then you don't need to come to the exam. So, but last year nobody was like this. But previous years there were people like this. So if you have close to maximal for homework, a maximal on colloquium, and then a few extra points from homework, you should be in this case. Okay. That, that's not the next.
Is this course for first 3 modules?
So if you're in software engineer, you have 3 modules. In applied math and informatics, it's 2 modules. And the third module is just 3 or 4 lectures about parameterized complexity. Then there are exercises that help you prepare for programming exercise. But for third module, there is only, the grading is only the programming exercise.
Okay, thanks. Because I have in my exams in second module exam, and the course is consists of 2 modules. That's why I asked the question.
Yeah. So in software engineer, so there is only one exam for everyone, and it happens at the end of second module in December.
Okay.
And colloquium is also, yeah. So please pay attention for people from software engineering, that exam and colloquium is not at the end of the course. Okay. So then let's start with what we need to cover. And there is less than 1 hour left, so I need to be fast. Okay, so let's consider, so there are problems that are very similar, but are much different in difficulty. And so one of them is called Eulerian walk problem, or Eulerian cycle problem. So imagine you have a graph with nodes, 5 nodes, and the question is, can you walk through all the edges? So there is Euler who lived in Kaliningrad. So it's a part of Russia. And there was a few islands with bridges. And so the nodes are islands, and the people were wondering, is it possible? So some tourist office, I guess, want to know, is it possible to make a walk through the islands and cross every beautiful bridge exactly once? So that was famous for being very beautiful bridges. But then there was, some bad things happened to the bridges, so they're not so beautiful anymore. So here is an example, and so can you make a walk? So that's also is similar. Can you draw this picture without lifting your pen? And so the answer is no. And how do you know this so fast?
Counting degrees.
Yeah. So here there is 4 nodes with odd. So if you make a walk, so every point that's not an endpoint, there you will enter and leave again. So each time you visit this node, the degrees increase in steps of 2. So that means if the answer is yes, then there must be at most 2 points with odd degree. But here are 4 points. But if I remove this thing, then it becomes possible. And because you can start here, go around, and then end here.
Can you walk 2 times the same edge?
No, that's a question. Can you do like a minimum of walking so that every bridge is visited exactly once? That's the idea. So this make a cycle so that every edge is visited exactly once. So this is pretty easy problem. Even if you get a graph of millions of nodes, you can check in a fraction of a second whether it's possible. And even constructing the walk is equally easy, almost equally easy. So you just in a greedy way create circles and then put them together. So if you connect 2 circles that share at least 1 node, then you go through 1 circle, then do the other circle, and then finish the first circle. So you can connect cycles. And so by just create a search for cycles, remove them from the graph in a greedy way, and then combine them in 1 big cycle, you get a Eulerian walk. So even production problem is pretty easy. But then there is a second problem. It's called Hamiltonian cycle problem. Given a graph, can you go through all the nodes? Can you visit all the nodes exactly once? So this is what it's called. It's connected to travel and salesman problem. So there is an island and a salesman who wants to visit every city exactly once. Traveling salesman problem is a variant where you also get distances between the nodes, and there is a point to minimize the total distance. But here you can see, so Hamiltonian cycle problem is a special case where distance are exactly of length 1. And so now there is the delivery man problem. And so you can use a few cycles. So you want to do the same thing as a traveling salesman. This is pretty important because so much delivery. There is also in industry where there are electronic circuit boards where holes needs to be drilled. And so the time of drilling the holes is proportional to the distance between the holes. And so people also want to have an algorithm to minimize the time of the drilling because equipment is expensive. So that if it's used optimally, they can use fewer drilling machines, and it's robotic drilling machines are pretty expensive. Okay, so it's similarly. Another problem is given a graph, let's use the same one. Can you color the nodes so that adjacent nodes have different colors? So that's a colorability problem. So K colorability problem, there's usually a fixed number K. So for example, 2 colorability problem. Can you color this graph in 2 colors so that every nodes connected by an edge have different color? So for this graph, is answer yes or no?
No, because it has
Triangle.
Yeah.
Yeah. But can you do it with 3 colors? So I can already start with the triangle because they need to have different colors. So, and then the answer is yes, because we can make this one red and this one black. And so 2 colorability problem, are 2 colors enough? Is solvable in polynomial time. So graph is 2 colorable if and only if it does not have odd length cycle. So whenever there is odd length, it's clear, right? You alternate the colors, but if the length is odd, this doesn't work. But if there is every cycle has even length, then it's 2 colorable. So you can think about why this is. So you use greedy algorithm. And why do you never get into a problem if you just pick one node and start to greedy color the neighbors? Let's say breadth-first way. Okay, so there are many problems that they look very similar, but you change a little bit and it goes from easy to hopelessly difficult. So no sub-exponential time is known for it. Okay, so in industry, there is something magic. Either it's polynomial or it belongs to most problems in practice, either polynomial or they belong to this class of NP-complete problems, which are difficult in a very strong sense. This is about industrial practice where combinatorial optimization is important. In theory, there are problems that are probably in the middle, like from cryptography, how to find an inverse of a function. Okay. Second thing I need to tell. So let's make a list of everything we will cover. So first one is easy versus hard problems. This is a bit philosophical. Then we have decision versus production. So it turns out, so we will distinguish polynomial time versus exponential time. It means we don't care about quadratic slowdown of algorithm. And if we look at this very high okay, algorithms, people, their ears is like, oh, wow, how can you not care about quadratic increase in time? It's outrageous for them. But for us, it's not outrageous. And at this level of looking at problem, decision versus production doesn't matter. So let us explain it with example. So imagine we want to find a clique in the graph. So this graph, it has a clique of size 3. It does not contain a clique of size 4. If these 4 nodes are not a clique because there is no connection in the diagonals. So there are 2 questions. Given a graph, the input is a graph K. Sorry. Let's take the Hamiltonian cycle problem. And so can you make a cycle that visits each node exactly once? Here the answer is yes. Imagine that you have algorithm that answers the decision problem. Then you also have an algorithm that produces the Hamiltonian cycle. So how is the reduction going? Idea is to iterate over every edge and remove this edge, and then ask again, does this graph have a Hamiltonian cycle? So for example, I delete this edge. Now graph, so if I have decision algorithm, I can run this decision algorithm and it will say, no, there is no Hamiltonian cycle. So then I know that this edge is part of each Hamiltonian cycle. And I can do it for all the edges. So for example, I can do it for this one. I can remove it and then ask again, does this graph have a Hamiltonian cycle? If the answer is yes, then I keep this edge permanently deleted. So I try to greedily delete all the edges as long as the answer is yes. And in the end, I will just get a graph that is a Hamiltonian cycle.
Sorry, can you explain, please, what is decision and what is production?
Okay. So decision problem, the input is a graph. And the question has Hamiltonian cycle. And the production question, so this is decision. And production, there is a question, produce Hamiltonian cycle. So here the answer is yes or no. Here the answer is a cycle, a list of nodes. So that subsequent nodes are connected.
Excuse me, is it true that if the graph has a Hamiltonian cycle, then there is an edge, so that every Hamiltonian cycle contains the edge?
It doesn't matter because you still get a Hamiltonian cycle in the end.
Why?
I think full graph on 5 nodes has 2 cycles that are completely disjoint. The star and the outer.
But we remove an edge if it belongs to
At least one.
Yeah. Well, no.
We remove it because it does not belong to any Hamiltonian cycle.
Yeah. Okay. Don't worry about. So it's interesting question. Your answer is correct. I think that also with 5 nodes you can have like the dual of the graph is itself, and therefore the clique on 5 nodes has 2 disjoint Hamiltonian cycles. So it's correct. It's very quick. You.
Sorry. So the
Yeah.
main difference is that if you answer a question about decision, you have only true or false.
Yeah.
If you answer the question about production, you have many different cycles.
Yeah. Answers can be.
Sometimes you have many different cycles. Yes.
Yeah. So in our course, we only consider decision, but when you work, you need production. So your boss doesn't care about if he has a car that needs to go and deliver things. He doesn't care whether there is Hamiltonian cycle or not. He needs answer. This guy needs to go there, and there. But
Okay.
yeah, I want to explain why, but this is easier to deal with theoretically with such algorithms. And now there in the seminar, there will be exercises to see that this is equally difficult because we don't care about polynomial time. So when you work about your bus and you have good algorithm, you will need to deal with these details, but they're logically. So we will only teach the part that people don't study by themselves, by nature.
Sorry, I have one question.
Yeah, so
So
you
they are the same because we don't care because we see that or we don't differentiate between polynomial time algorithms.
yeah, exactly. So if this is solvable in quadratic time, this is solvable in cubic time. We
And
understand.
they are equivalent because of that, because we
Yeah,
don't
yeah.
differentiate between polynomial time algorithms.
Yeah, exactly. But
Okay.
when you work in research, probably your boss will care. He will tell you solve this in less than 1 second. And then you can solve this in 1 second, but this will take 100 seconds. And so you will need to do the last step of optimizations. But you want to stay outside. So when it's NP hard, you will need to run solvers. And but solvers are unreliable. So something might change from the problem in practice and suddenly solvers stop working. And it's very annoying situation. So if you can give your boss exact algorithm, that's always guaranteed to work if the input is not too big. So if slowly over time the input gets a bit bigger, then boss slowly sees that the algorithm gets a bit slower. But he can be reliable if he doesn't. He can do whatever change he wants as long as the input doesn't get bigger. He can be confident algorithm will keep working, and especially competitor will not have better algorithm if it's optimization problem. Okay, so. So in seminar, there are more questions. So so there was also the clique question. Given a graph, find the biggest clique inside the graph. And here, decision problem will be, so the decision problem has has a graph and a number k. And the question is, exist clique, a set of nodes in the graph of size at least k. So this is the decision question. And then the production question will be find clique of maximal size.
Not of size k.
Yeah, the size is usually not given. But it's not a big problem. So if the size is not given, what will we do then? So if we have an algorithm that solves the decision question, so how do we will get the maximal size of the clique?
Binary search.
Exactly.
Then just remove one.
Yeah. So that's just logarithmic overhead. This binary search is definitely not a big deal. Okay, and then we will have the max size, and then we want to produce the clique. So that's for seminar. Yeah, but by the way, while we're talking about seminar, before the lecture, I update the second homework question. So I read again and I noticed it's now extra question, the old homework question. I just used the last version, I'm saying, from the wiki. Okay. So that's prediction versus decision. Now we will speak about our computation model. It's Turing machines. So if it's important to measure the time very precisely, you will use a RAM model, like an algorithm scores. when you quadratic cubic is important, then it's basically counting elementary operations. So they say we can solve this problem, we can solve sorting with this many comparisons, we can multiply matrices with this many additions and multiplications, and so on. But here we have specific mathematical model. It's Turing machine. It's very simple model, but it's equivalent to RAM model up to polynomial in the runtime. Okay, and so you already know about Turing machine. So it's a device and it consists of two parts. So there is computation head and there is a tape. So tape consists out of infinitely many cells. And in the beginning, there is kind of program here, some input P1, P2, and so on, P, length of P. And so it can receive, so the task of Turing machine is transform one string to another string or receive a string and say yes or no to answer decision question. So there are two uses. Most of, in the first leg, for example, I will use string to string mappings to get used to the model, but then afterwards we will use it as a decision machine. And so here is computation head. And this computation head, it can move. So every computation step, so they're the same step. There is only one elementary operation in this model. That's why we like it so much. And so we want to prove that one computation is harder than another one. And one problem is harder than another problem. And what we will do is simulate one problem inside another problem somehow. And therefore, we want a computational model that we can easily embed into other problems. That's why we use Turing machine with just one elementary operation. In RAM model, there is like 10 or whatever elementary operation. So each time we need, if we would use this, each time in a proof, we need to go through all the elementary operations and see that we don't make in the reduction a mistake. Okay, sorry, but I'm flipping from motivation to actual explanation, which is not good. So we have a computation head and a tape. And the elementary operation is read, write, move. So in each step, the machine will scan the symbol below its computation head. So a symbol will belong to tape alphabet, which is, and alphabet means finite non-empty set. And so each tape cell contains a symbol from tape alphabet. Computation head reads it. Here there will be a state. Also from a set of states, finite set. And depending on state and scanned symbol, it will write something and move somewhere. So that's what's happening.
But don't you think that this is not one simple elementary operation? It's 3 or 4.
Yeah. So one elementary operation consists of 3 parts: read, write, move. So
And
depending
move
also on what is read. Yeah.
Okay.
Yeah. And so here there is a transition function. And so the transition function get us input element from alphabet and also the state of the machine. And it will output, so what it writes. Sorry, so it will output, let's flip the order. Let's see, Q gamma, it will output what it writes, how it moves. It either makes a left or a right move. And what's the new state? So this will control the behavior of the machine. So let's do an example. Let's have a machine that has only one state, and in every state, let's make a machine that produces identity function. So this machine will have just one state, Q, will be equal to just the start state. And delta of S might be equal to the triple S plus of 1 S. Sorry, what I'm writing here. So it will write, sorry, I'm writing nonsense here. So S0 will be equal to 0, 1 S. Delta S1 equals 1 plus 1 S. So this is a completely useless machine. So it receives a program and it will output the same program. And we need this
Termination.
yeah, sorry. So what is gamma? Yeah, sorry. I need to say what is gamma. And also, so usually the program is a bit string. And the tape alphabet, it's mandatory that it contains a blank symbol. So I will write a formal definition after I explain it. So in our simple useless machine, the tape alphabet contains 3 symbols. And the rule is that tape alphabet is completely filled with blanks, except on initial segment, where it contains a program without blanks. Okay, so this is machine that, okay, and delta is partial function. So delta blank is undefined. So when transition function is undefined, the machine stops. When the machine stops, we may look to the tape, and then the first word is the output. So the first set of symbols that terminates at the first blank will be the output of the machine. There is also another thing. If machine is on first cell and move left, then nothing happens. An official definition.
Doesn't the official definition have a tape that's infinite in 2 directions?
There are many definitions, they're equivalent, but in Zipser book and this book, they use one-way infinite tape. Actually, I'm not sure about this book. But actually, I'm not sure about other books, but I thought that in the books, yeah, it's the same. So the same function are computable, just a polynomial change in the runtime at most. Actually, logarithmic factor, the runtime fixes changes by logarithmic.
So we define termination as just an action. So
Yeah, but
not
the logarithmic is a hard proof. So it's in chapter 1 of Zipser.
Chapter 1.
Yeah. So yeah, that's why I recommend to first read in Zipser book, and when you can do the exercise as well in Zipser book, then move to Aurora and Barak.
Sorry. So what is the initial position of the Turing machine?
Okay. So initially, so there is a special state, the start state, and initially the computation has the start state. And the head is located above the first cell. So that's how the machine is started.
So you define for this problem exactly that the Turing machine is on the left on the tape.
Yeah.
And in another problem, you can put it in another position.
Yeah. So let's do an example. So let's consider a machine. I will write, so with 2 states. So I will write a machine that prepends 0 to the string, to its input. And it will have 2 states. It will have, I will call it as 0 and as 1. And so the plan is to have a word and to prepend 0 to the word. That means that every bit needs to be transferred to the right. So I will use 3 states as prime for the beginning. And then there will be a transition. So when S prime sees a 0, it will write 0 and move to the right. So that's how you can make schematic presentation of Turing machine. When it sees a 1, it will so when it sees a 1, it will write 0 and move to the right. So that will be the plan to construct this Turing machine. So when it's an S0, it will always write the 0 and move to the right. But when it sees a 1, it will move to S1. So that's basically the finite memory of computation head. So ideas computation head has finite memory. And then we do the opposite. So when we see 0, we write 1R. When we see a 1, we write 1R. And here we write, when we see a 0, sorry, I forgot. 0, 0R, like this. So now do you see why 0 is prependent to the output? And so let's do a detailed example. So here is a description of computation head. And so here in this thing, we will have finite set Q.
Sorry, if you see bottom, you stop.
Yes, yes. Okay, please, your question.
In this transition automata, if you have a bottom, you transition to what state?
So here is the start state. The start state will be S prime. And then when we read 0, we will write a 0, go to the right and go to the state S0.
I mean, what if you see bottom on the tape?
Yeah, sorry, when there is a blank. Yeah, sorry, good question. Yeah. Then it's undefined and the machine stops.
Okay.
Yeah.
So I forgot.
Yeah. So it's the same here, like here, but for all the S. No, it's very good. I should have told this.
But you have explicitly tell that your machine starts on the first symbol.
Yeah. On
the left. Yes?
Yeah.
I mean on the tape on the left.
Yeah. The machine.
Because if machine starts on the right, it will not produce correct output.
Yeah. It's part of definition. When we start the machine, we will always start in the beginning. But in the definition, we also need to say what is the start state. So the formal definition is 5 tuple. So first, the set of states, then the tape alphabet, then the transition function, the start state, and 4 tuple. Well, in Sipser book, there is another symbol. It's called sigma. And it indicates what are allowed to be the inputs of the machine. So sigma must be a subset of gamma.
Gamma power n.
Gamma is tape alphabet. So the machine can write symbols that are not part of the programs.
All finite sequence of
Yeah. So input will be sigma star. But while it computes, it may use more symbols. So that's why Sipser book has extra symbol here to make things formally correct. But some people drop the sigma from the definition and just say, okay, this machine works if you give it problems of this type. So it's about how to use the definition. Okay. So but first, let's do example on certain input here. And so what will our machine do? So I will just draw the tape with computation head above it. So if I have 0, 1, 0 followed by blanks, so initially our machine will be in state S prime. Oh, okay, let us now write the machine in the example. So we have S prime, S0, and S1. Gamma is 0, 1, and blank. Delta, I will not write it. It's according to the scheme, right? So there are two inputs, the state and the thing before the bar. Output of delta, and so delta C scheme. Then the start state is S prime, and sigma is the input are words over 0, 1. Okay. So here, after the first step is completed, we will have machine in state, sorry, S1 here, and it will be above the second tape cell. So if read write operation is finished, we will have 0, 0, 1 on the tape, and machine will be here in state S1. Right.
Please change the mark.
Yeah. Like this. And so what will we have on the second step? After the second operation is finished, what will be
A 0 above the third element, and there will be 1. 1, 1, blank.
and here we will have S0.
So the state is just some state of the head and nothing to do with the position of the head.
Yeah. So state is element of Q.
So it's just some set that the head can be in this set of states.
Yeah.
And it doesn't, it's nothing have to do with the position of the head.
No, state is element of the set Q. So let us say what are formal requirements on type form. So we say that Q gamma delta S prime of just S sigma is a Turing machine if so Q finite non-empty. So there are the two requirements. Gamma must contain a blank symbol because we want to define the tape at the initial moment containing all blanks, but in the beginning a string.
And also finite.
Yeah, also finite. Yeah, good point. And finite.
And where is in this formalization the initial position of the head, or it's just implicitly assumed that?
Yeah, this is always in the beginning of the tape. That's why we use one-way infinite. Then there is a natural position. Okay.
Okay, thanks. I
yeah.
got it.
Yeah, so delta is a function of this form here. So see above. S is an element of Q, and gamma, sigma is a subset of gamma minus the blank symbol. So they're formal requirements. And then I will not write formal definition of elementary operation and input of a string of sigma, right? A sigma will almost always be binary alphabet. There is also in the seminar one case where we consider unary alphabet. So then, so a number in unary is just the symbol repeated that many times, the value of the number. Okay, that's for a seminar. Now, so this is very simple model, but it's very good model because anything you can do in a program, in typical programming language, machine can also do. So for example, you have programmed one function using Turing machine, and you want concatenate with another function. It's very easy. You just take the computation head from first function, Then you let it work until it's finished, so it reaches undefined state in delta. And then you will transfer to another machine that goes back to the beginning. And then you start the computation of the other flux. So composition is easy, but then also recursion is easy. So you have for loops. And so it should be easy to believe that this machine, okay, maybe not so easy. So I hope you believe you can do everything with a little bit of fantasy. It should be believable. If you want to prove this formally, okay, this is an annoying task. Okay. So then there also exist variants of the machine. Also a Turing machine can simulate other Turing machine. Why? It's easy to think of a Python program or whatever, C++ program that simulate Turing machine. But you also know that Python program can simulate any other. But we argued a little bit that Turing machine can simulate Python or C++. So since it can do for loops, it can do while loops of functions. So this is kind of believable. So when you think about Turing, you should just think about Turing. Okay, now there is another question. We were talking about problems with graphs, and Turing machines can only get strings as input. So that means that in order to relate a model with our actual problems, we need to encode our objects in binary. And so when we're given a graph, we can associate graph with adjacency matrix. So if we have a graph with n nodes, we can associate it with just n squared bits. Yes. So if you have a list of words, again, if the length of the words is fixed, then it's really easy to associate them. So you need to think a little bit how you will encode the length of the words, but you can also start with prefix-free encoding. So numbers. So for numbers, we use prefix-free encoding. So for example, we can think about the machine that performs addition. So addition will be performed on the machine in quadratic time. Okay, let's also think a little bit about palindrome. So palindrome is a word, if you write it backwards, it's the same word, like kayak in natural language, but the same in binary. So this is palindrome. So we can build a Turing machine that recognizes palindromes. How long will it work? How many elementary steps will be needed? Will it be linear, quadratic, exponential?
It will be quadratic because we move them back linear many times.
Yeah. So if you implement it, we will look at the first bit, replace it by a blank, then search for the last bit of the input. So here are blanks. Replace it as well by a blank and check whether it's the same as the first one. And so we will have states to remember 0 and 1, and then go back and forth. So the runtime, so if we get a word of n bits, the runtime will be on the first, we have to make n plus 1 moves, then n moves, n minus 1 to go back and forth. Sorry, 2 times. We will have 2 times n minus 1 and so on. And so it will be order n squared, quadratic time.
Is this proved to be optimal?
Yes.
In chapter
And why we care about the difference between linear and quadratic?
Yeah. So it's up to constant because you can also remember several symbols, and so you can speed up indeed. But the speed up, you can only remember a finite amount. Sorry, Eldar, can you repeat your question?
Why we care about the difference between linear algorithm in Turing machine linear and quadratic?
Okay. I only care because it's your first, for many people, it's first time we deal with Turing machine, and I want to check whether you can reason about them.
Okay.
It's just exercise.
Because I thought that we only care is it polynomial or not.
Yeah, you're right. You're fully right, but we just care in the first lecture. The first
Okay.
time. Yeah. Okay. So this is Turing machine. Now we can build a Turing machine that simulates others, so that gets two strings as input, separated by blank. First string will be the code of another Turing machine, a binary encoding of the delta function of other Turing machine. And so on. So there is a machine that takes code of other Turing machine and simulates other Turing machine on the second argument.
Normally we can't use that symbol as an input.
Well, we can define we can define functions from Turing machine with two inputs, and then we can say, okay, let's it's a formal question. I agree that most authors will say, let's use one input and append another splitting symbol in sigma or in gamma. Okay, yeah. Yeah, so this is called universal Turing machine. So I will not write the definition, it takes too long, and the lecture, I guess, 10 minutes left. So I will say a few other things. So there also exist two-tape Turing machines. There are Turing machines that have several tapes. And only one tape, the first tape contains a program, and initially the second tape contains only blanks. And they have two read-write heads. And so for these functions, the transition function, so we can have k tapes, any number of k. So if there are k tapes, then the transition function is the same, except that we have k moves. The read-write heads can move individually. They can write different symbols on all the tapes, depending on what is read on all the tapes. And so all the tapes, the symbol of the below the computation heads are read. They go to the computation head. Depending on the state, there are new write and move instructions for all the tapes.
Can it stay in place in at least one tape?
Well, this is equivalent. So if we add 0 here, so representing no move. So you can think that this is the change in position. Then you can add 0 and the definition remains the same. So the runtime changes by additive constant. Because you can always replace, or even factor 2, let's say factor 2. Because no move can always be replaced by write, move, and return back.
Yes, but then you run into parity issues where odd cycles always correspond to odd positions on the second tape.
Yeah, but the machine can just write
Just
what
only
it
use given
reads
position
in the
function.
odd position. And just the machine is twice slower, but mathematically nothing changes. Okay, so now let us think on two-tape Turing machine and our problem of palindromes. So palindromes, remember we have to check whether reading backwards gives the same string. Can we do better for two-tape Turing machine to decide palindromes?
Yes, we can copy the input on the second tape and then.
Yeah, and then have the read-write heads going in opposite directions until you're at the beginning. So there is a formal issue, like first you have to mark the initial position. So you can consider a Turing machine that has two copies of the tape alphabet. So so a copy of the marked symbol. And so the first thing you do is place a mark. So replace the symbol by the marked one on the first element, so that you always know when you finished returning, so the machine can halt and decide. Okay, so here we are using Turing machines for deciders. So decider Turing machines, they have two extra the things. There is a reject state and an accept state. And so an input is accepted if machine halts in accept state. it's rejected if it halts in reject state. So a machine decides a language if on every input from sigma star, so sigma star is all finite lists of symbols in sigma. So is it known for software engineering, this star notation? Do you know this? No reaction, so I assume this.
It's alphabet.
Yeah. So sigma is alphabet and sigma star are all the strings of alphabet. So sigma is non-empty finite set. And sigma star is all, for example, the binary strings are empty strings. So this is 0, 1 star is equal to empty 0, 1, 0, 0, 0, 1, and so on. Right? So this set okay. So a string is a decider for a language. So a language is just a subset of sigma star. So a machine decides a language if for okay, we don't need this. Yes, we don't need. So that fixed terminology. So machine Q, gamma, and so on. That sigma Q accept, Q reject. So I'm writing a definition. Decides, and the marker is that here. Decides L, which is a subset of sigma star. If, for example, palindromes is a set of words, and here I let's say sigma star binary alphabet. So that is considered binary palindromes, for example. The machine decides palindromes. Here we have US. Decide sigma if for every word in L and machine halts in state Q accept, and for every word inside sigma star minus L, the machine halts in state Q reject. So this is definition of decider. Yes.
And the sigma star is all possible substrings that you can create by using gamma alphabet.
Yeah.
Then why is finite? It's not finite.
No, sigma is finite, sigma star is infinite. Yeah. So sigma for binary alphabet, sigma is 0 and 1. Sigma star is empty string 0, 1, 0, 0, 0, 1, and so on. Okay. So that's what it means for definition to decide. And now the last thing we need to say is how we define the class P, problem solvable in polynomial time. So, or let us more generally, let us say what is, I will, or maybe I should leave this. So the class, so given the time bound, for example, linear. Let so here we have a function from natural numbers to natural numbers. For example, identity function, when we speak about linear time. And then we define the class time f of time f, the division problems. And this is just, it is class is the same as set, but when we use set of set, Then we use the word class or collection because sometimes it's a bit confusing. So time is class of decision problems. So a decision problem is a set. So here L is a set or a class of languages for which exists a Turing machine running in time order f of n. That's on input W decides language time order f of length of W. So here is so the time of f. So a language is in time of f, for example, linear time. If there exists a Turing machine that on input some string W decides the language in time order f of length of W. For example, we just proved that polynomial time machines are belong to the class of linear time functions. So when we choose f of n equal to n, we have linear time bound. Palindromes belong to this class because there exists two-tape Turing machine that decides this language using order f of length of n steps.
Time is defined using two-tape Turing machines.
In Sipser book, it is one-tape Turing machine. In Aurora Barak book, it's any number of tape. Yes, and in some proofs, I will choose one-tape Turing machine to make everything easy. So it's a tricky question. But okay, don't worry. In exam question, you can pick any definition. I will on colloquium or exam. I will remember about ambiguity. So just pick definition you like the most. Okay, so now we understand what is time of f. We can also define space of f. It's the same way, but now machine can use at most f of input, order f of input, many tape symbols. So you can like cut apart from all the tapes. So actually they use the sum of the tapes, but usually the tapes are constant. So when you look to a fixed Turing machine, the number of tapes is constant. So here, when you fix a Turing machine, the constant of number of tapes goes inside here. So, for example, the click problem can be solved in linear space. So let's break this down. So how does it work? So we receive a graph, or let's take Hamiltonian cycle problem. So why can we solve Hamiltonian cycle problem in linear space? So for this, we get the graph. We need to think about the input size of the graph. It's quadratic and the number of nodes. Okay, and how can we check whether there exists Hamiltonian cycle by brute force? We just write down all lists of nodes, all permutations of nodes, and then check whether all subsequent nodes are connected. And also whether the first and the last, it depends. We have Hamiltonian path and Hamiltonian cycle variant. So in path, you can have different, the first and the last can be different. In cycle, the first and the last node must be the same.
That's
Okay.
n log n.
Yeah, because of
Yeah.
long numbers.
So if we have n nodes, we have indeed n log n space needed. But the size of the input is n squared. So then we indeed have linear size for the memory.
Linear in input size.
Yeah, linear in the input size. So be careful. N by default, it means the length of the input, but sometimes people redefine it. So they say, give an algorithm for example, I can ask, give an algorithm that solves Hamiltonian cycle problem in space on graphs with n nodes in space n log n. And then it's a tight bound. Okay. Yes, so you need no time f space f. And then let's define what is p. It's almost finished the lecture. Oh, I'm 5 minutes late. Let's delete it. So there is class of polynomial time problems. And this is union of time n to the power c. So for natural number c. Then there is also the class x. It is equal, and here you need to remember something. Because, sorry, this is wrong definition. So I will delete it, but sometimes people make a mistake. It is n to the power c. So know that an exponent bracket should be here, right? By default. Okay, so this is the class x. And then similar, we have p space and x space. As the union of space n to the power c and x space. Okay, I will not write it, but you can guess it, right? So, and then there are certain relations.
What is x space? I couldn't guess x before.
Yeah. So the same as p space, but 2 to the power n to the power. Okay, now I've written it. And so there are certain relations. So p is a part of p space. If you can solve something in polynomial time, you can solve it, well, more generally, time space f is part, time f is subset of space f. Okay. So if you have a limited time, if you stop at f of n elementary steps, then you can use at most one cell more. So the maximal position is at most one cell more. This is clear. But the reverse is usually not an open question. Only if the time bound is really huge, we know that it's equal. So that means that space is much more powerful resource because you can reuse it.
Really huge means the exist function f, so that we know that space of f.
Yeah, I think so. I think as soon as you're double exponential, no, so sorry. No, I'm wrong. It's always unknown, sorry. Yeah, so p space, but p space is a part of x. And x is, of course, a part of x space. Oh, there. So here, we will need to prove that p space is a part of x. And this proof, I think it's part of seminar prepares for this observation. So we will explain it in the next lecture. Okay, so next lecture will be difficult topic. So we will prove that so if f is bounded by g divided by log of g, so if we have two time bounds, then we will prove that time f, well, let me say it differently. Next lecture, we will prove that p is not equal to x. And we will prove that p space is not equal to x space. So that's like only thing that's known in computational complexity when classes are provably different. So we will use diagonalization technique, and that's the only technique that actually worked to prove that something different. For the rest are open questions. Okay. So see you on Wednesday evening. And there will be seminar in other room, but I don't remember which room. So can somebody tell it? Where is the seminar?
G115.
Yeah, G115. Okay, I will tell seminarists to start 10 minutes later, then so you have 20 minutes for resting.
So you start in 20 minutes.
Yeah, in 20 minutes. Okay. Thank you for all questions. Alder, it's very good you ask many questions.
Thank you for lecture.